In 1926, a French inventor filed patent CH118648A in Switzerland. The document described a device composed of nothing more than copper wire, magnetic steel plates, and geometric coils. No fuel, no chemicals, no moving parts, just metal arranged in specific patterns, buried in soil. The patent claimed this apparatus could triple agricultural yields by capturing atmospheric electricity. Official field trials reported oat stalks growing to 5 feet tall, dying trees bursting back to life, pumpkins the size of barrels, cabbage heads taller than children. The British Ministry of Agriculture established a committee in 1918 specifically to investigate these claims. For 18 years, they collected photographs, yield records, and testimonials. Their files, stamped "not for publication," documented results that contradicted every principle of conventional agriculture. By 1936, the technology had vanished. The committee disbanded. The research went silent. And within 2 decades, the global fertilizer industry grew from 1 million tons to over 20 million tons, establishing a subscription model that continues today. This is the story of Justin Christofleau, the atmospheric energy he claimed to harness, and the economic forces that required his work to be erased from agricultural history. Born in 1865, he was not an academic. He was a farmer who spent decades conducting experiments. He noticed that crops grew differently depending on their proximity to metal structures. Rows near iron fences produced heavier yields. By 1920, he had constructed elaborate systems of copper spirals and magnetic rods. He kept meticulous records, photographing harvests, measuring stalk heights. On October 26, 1925, Christofleau filed his patent in Switzerland rather than France. The choice was deliberate. Swiss patent law offered stronger international protection. The patent document contains precise technical specifications. Copper plates measuring 30 by 40 centimeters. Magnetic steel rods 1.2 meters in length. Spiral coils with specific turn counts. Christofleau called it the Appareil de magnetoculture terrestre celeste. The name reflected his belief that agriculture was a matter of electromagnetic relationship between earth and sky. He invited skeptics to visit his fields. For Christofleau, transparency was essential. He was demonstrating a principle of physics that he believed had been overlooked for centuries. The photographs that circulated in French agricultural journals between 1920 and 1930 showed harvests that seemed impossible. Cabbages with heads 60 centimeters in diameter. Pumpkins weighing over 50 kilograms. Corn stalks reaching heights of 3 meters. These images appeared in publications like Le Jardin Praticien and Revue Horticole, often accompanied by Christofleau's detailed captions. The photos were not isolated incidents. Multiple experimenters across France, Belgium, and Switzerland reported similar results when replicating Christofleau's methods. A gardener in Brussels documented potato yields 40% above regional averages. A vineyard owner in Geneva reported grape clusters twice the normal size. The visual evidence accumulated, but the photographs alone proved nothing. Without independent verification, without soil analysis, the images remained compelling but inconclusive. Critics pointed out that selective photography could explain the results. What was needed was institutional validation. The British Electroculture Committee provided it. Established in 1918 under the Ministry of Agriculture and Fisheries, the committee's mandate was to investigate claims. This was not a fringe operation. It was funded by the British government, staffed by credentialed agricultural scientists, and tasked with separating legitimate innovation from pseudoscience. Between 1918 and 1936, the committee collected field reports from across Europe. They reviewed Christofleau's work extensively, along with experiments by other electroculture pioneers. Their interim reports, stamped "not for publication," documented yield increases ranging from 20% to 50% in trials where electromagnetic apparatus was used. The committee's files contained photographs, yield data tables, soil composition analyses, and weather records. They sent observers to Christofleau's gardens in France. They requested samples of his produce. They examined his equipment and reviewed his methods. The documentation was thorough, methodical, and official. Yet despite 18 years of investigation, the committee never published a final public report. In 1936, the British Electroculture Committee was quietly disbanded. Their files were archived, marked for restricted access, and removed from general agricultural reference materials. The research that had occupied government scientists for nearly 2 decades simply vanished from public discourse. The visual record of giant vegetables and the institutional validation of a government committee created a historical paradox. Either the technology worked and was suppressed, or the evidence was fundamentally flawed. Every square meter of the Earth's surface sits beneath an invisible voltage gradient. The atmosphere and the ground maintain a constant electrical potential difference of approximately 100 volts per meter of altitude on clear days. The ionosphere, the upper layer of the atmosphere, carries a net positive charge. The Earth's surface carries a net negative charge. The potential difference creates a vertical electric field that permeates the air we breathe. This field is detectable with simple instruments. A voltmeter connected to an antenna elevated above ground will register the voltage difference. This atmospheric electric field is not theoretical. It is documented in physics textbooks, measured by meteorological stations worldwide, and studied by atmospheric scientists as part of the global electric circuit. Plants grow directly within this field. Every blade of grass, every tree, every crop stalk extends from the negatively charged earth into the positively charged atmosphere. The plant itself becomes a natural conductor. Leaves, covered in microscopic structures and surface moisture, collect atmospheric charge. Roots, embedded in conductive soil, connect to the Earth's negative pole. This is not speculation. Measurements taken with electrodes inserted into plant stems show that electrical currents flow through living plants. Studies conducted in the 1960s and 1970s documented millivolt level potentials. The plant acts as a living antenna, continuously interacting with the Earth's electric field. Christofleau's apparatus was designed to amplify this natural process. Copper, being far more conductive than plant tissue, could collect atmospheric charge more efficiently than leaves. A copper wire or plate elevated above ground creates a low-resistance pathway for atmospheric electricity to flow into the root zone. The magnetic steel components in Christofleau's design were intended to focus and direct this current, similar to how a magnetic field can guide the flow of electrons. In 1913, 2 German chemists, Fritz Haber and Karl Bosch, perfected a process for synthesizing ammonia from atmospheric nitrogen. Initially developed for explosives, it became the foundation of the fertilizer industry. By 1920, factories were producing synthetic ammonia at industrial scale. Production costs dropped. By 1960, global production surpassed 20 million tons. Today, it exceeds 180 million tons. The economic model was revolutionary. Farmers could purchase soil fertility in bags. No need to rotate crops or rest fields. Just apply ammonia-based fertilizer and watch yields increase. But there was a dependency. Synthetic fertilizer depletes soil health. Over time, soils lose organic matter and structural integrity. Yields become dependent on continuous application. This was the business model. Farmers became subscribers, purchasing fertilizer every season. The entire food system became locked into a cycle of dependency on chemical production. By the 1930s, the industry represented billions. Any technology that could produce yields without purchased inputs posed a direct threat. If a one-time installation of copper wire could replace annual purchases, the financial implications were catastrophic. By the mid-1930s, references to electroculture began disappearing. Journals stopped accepting submissions. University researchers found their funding cut or redirected to chemical fertilization. The British Electroculture Committee was disbanded in 1936 without explanation. Their files were archived in restricted storage, unavailable to researchers for decades. Textbooks published after 1940 dismissed it as pseudoscience. The narrative shifted. What had been a subject of serious government investigation became a cautionary tale about pre-scientific gullibility. The suppression was economic and institutional. Funding flowed where the profits were. Researchers pursued careers in fertilizer because that's where the jobs were. Publishers printed what the establishment endorsed. Christofleau's work was not disproven. It was simply ignored and allowed to fade. Within a generation, electroculture had been effectively erased from the agricultural mainstream. The search for modern evidence would require a test at a scale large enough to overcome dismissal. That test would come from China, where different economic incentives allowed for experiments the West could not afford. In the early 2000s, researchers at the Chinese Academy of Agricultural Sciences began investigating atmospheric electricity. China faced severe challenges: soil degradation, water scarcity, and the need to feed 1.4 billion people. The Chinese team designed an experiment at an unprecedented scale: 3,600 hectares of farmland, equivalent to 6,000 football fields. The trial included rice paddies, wheat fields, and vegetable crops. Over the fields, they suspended high-voltage wires connected to transformers. This was active electrical stimulation, not passive electroculture. But the principle was the same: enhancing the atmospheric electric field. The results were published in agricultural journals. Yields increased by an average of 20% to 30% across all crop types. In some trials, the increase exceeded 40%. But the most striking result was pesticide use dropping by 70% to 100%. Farmers reported dramatic reductions in insect damage and disease. The plants appeared healthier and more robust. Independent verification confirmed the results. Soil samples showed no hidden fertilizer. Weather records confirmed identical conditions. The only variable was the electrical treatment. The data was public, reproducible, and statistically significant. This was not anecdotal evidence from a backyard garden. This was institutional science conducted at a scale that fed millions. Yet the results received minimal attention in the West. No major universities or government agencies initiated comparable trials. The research existed in a parallel world, acknowledged but ignored. The question is why? A technology that could reduce fertilizer and pesticide use by 70% while increasing yields should have triggered a revolution. But revolutions are determined by who benefits and who loses. In this case, the fertilizer and pesticide industries had far more to lose than the farmers had to gain. Not all electroculture methods are the same. The distinction between passive and active systems is critical, both for understanding the technology and for safety. Passive electroculture, like Christofleau's apparatus, uses no external power source. It relies entirely on the natural atmospheric electric field. Active electroculture, like the Chinese experiments, uses powered electrical systems to create strong electric fields. Wires are suspended above crops and connected to transformers that apply thousands of volts. Active systems produce more dramatic effects because they deliver more energy, but they also carry serious risks. High-voltage equipment can cause fatal electric shock if mishandled. For backyard gardeners and small-scale growers, passive systems are the appropriate choice. They pose no danger, require no technical knowledge beyond basic orientation to magnetic north, and cost almost nothing to construct. A passive electroculture system can be constructed in an afternoon with materials available at any hardware store. Start with 14-gauge bare copper wire, approximately 1.5 to 2 meters in length. Using a wooden dowel 12 to 16 millimeters in diameter as a form, wrap the wire into a loose spiral with 4 to 6 turns. Drive a wooden or bamboo stake into the soil near the base of your plant, approximately 10 to 20 centimeters from the stem. Attach the copper spiral to the top of the stake. The spiral should be elevated 30 to 50 centimeters above the soil surface. The critical step is orientation. Using a compass, position the spiral so that the top end, the end of the wire that points upward, faces magnetic north. This is not symbolic. The Earth's magnetic field runs north-south, and aligning the spiral with this field may influence how effectively it interacts with atmospheric currents. The bottom end of the spiral, the lower terminal, should extend downward and be buried 10 to 15 centimeters into the soil near the plant's root zone. This creates the conductive pathway. Atmospheric charge collected by the elevated spiral flows through the wire into the soil, where roots can interact with it. For comparative testing, install spirals near half of your plants and leave the other half untreated as controls. Record measurements weekly: plant height, leaf count, leaf size. The cost of materials is typically under $10 per spiral. The time investment is minimal. The risk is zero. For anyone willing to conduct a simple experiment, passive electroculture offers a low-cost test of a controversial technology that institutional agriculture refuses to investigate. Whether it works in your garden is a question only your garden can answer. But the fact that the question is worth asking is enough to justify the experiment. The harvest of the future depends on whether we choose to rediscover what we were taught to forget. Whether a simple copper wire, oriented to magnetic north and buried in the earth, can still do what Christofleau claimed it could in 1926. The experiment is available to anyone. The materials cost less than a bag of fertilizer. The method is documented in archived patents and suppressed committee files. The only question is whether you are willing to test it. Because if it works, even partially, it changes everything we have been told about what is necessary to feed the world. And if it does not work, the cost of trying is negligible compared to the cost of never asking the question. The botanical evidence does not lie. The paper trail is clear. The physics is documented. The economic motive for suppression is transparent. What you do with this intelligence determines which category you fall into. Those who continue subscribing to dependency, or those who plant a wire and wait to see what grows. The files are open. The experiment is simple. The only thing standing between you and the answer is the willingness to try. Next excavation drops soon. The suppression goes deeper than agriculture.